So this is the pre-lecture video for day 5. And I chose to concentrate on relative velocity because I have a feeling we might not get to this in class. So you probably have an idea of what we mean by this. The relative velocity is when you're measuring your velocity relative to something else, and that something else might be moving. For instance, if you're driving down the highway in your car and you're passing someone, you might think about how fast you're moving relative to the car that you're passing. That speed is going to be slower than your actual speed because of the fact that the moving car that you're passing is also traveling. So say he's going 50 and you're going 65, you know that your velocity relative to him is the difference, which is 15. That's the kind of thing we're going to talk about in this section. So the first thing is we need to understand what we mean by the frame of reference. The frame of reference, again, is sort of what we're measuring things relative to. And when we're talking about relative velocity, we're going to have two different frame of references. Most of the time, one of our frame of reference is going to be stationary. For instance, here's a person who's just standing here. His frame of reference is the ground, and he's not moving. So his frame of reference, I'm using that abbreviation, is stationary. And we're going to call that the ground. Now the truck is moving, and this guy is standing in the truck. So the truck can be a moving frame of reference. In fact, the speed that the truck is moving with is 15 meters per second. These two letters here mean the velocity of the truck with respect to the ground. And then the guy that's in the truck is throwing a ball. Notice here, this means that we're measuring the velocity of the ball relative to the truck. So to this guy, the ball is only moving with 8 meters per second. But can you figure out how fast this person right here would see the ball be moving? How about 23? It would be the speed of the truck plus the speed of the ball relative to the truck. Let's see if we can figure out how that works. So we have another example of a stationary frame of reference here, and that is the cyclist. And the train, again, we like trains in physics, get used to it, is the moving frame of reference. And then we have the passenger. She's walking in the train. We can measure her speed relative to the train, or you might want to measure her velocity relative to the ground. There's two choices. Now in terms of the graph is trying to demonstrate this. Here is one frame of reference which represents the cyclist frame. That's the stationary frame of reference. It also we might think of it as the ground. Now if you're in the train, your frame of reference is moving. In fact, right here is how fast it's moving, the velocity of the train with respect to the cyclist. That's the velocity. That's also the velocity of not only of the train, but of its frame of reference. Now here is the woman who is in the train. This is her position relative to the origin of the train. This is where she would be if we used the train as the frame of reference. But if we measured her position relative to the cyclist, this would be our origin over here. We can not only measure her speed with respect to the train, we could also measure her speed with respect to the cyclist. Now here, these are all position vectors right here. This is the position right here, is the position of the woman with respect to, that's what that stands for, the cyclist. This is the speed, this is the position of the woman with respect to the train. And here is the position of the train with respect to the cyclist. Notice in this picture that the position of the woman with respect to the train, I'm just trying to use notation that's the same as what you see in the graph, is equal to the position of the train with respect to the cyclist plus the position of the woman with respect to the train. And that's just because this long line adds up to be these two added together. Sometimes it's going to get confusing to see how these two work together, but I like to sort of think about these subscripts here and notice that if I put these two together, the B's would cancel out and I'd get the woman with respect to the cyclist. The P and the A would remain, and you see that that's over here. We can also, this is a position expression that relates all of their positions. We could also take the derivative and find out how the velocities of everything are related to each other. Right here, this is the speed of the woman with respect to the cyclist. This is the speed of the woman with respect to the train, and this is the speed of the train with respect to the cyclist. If it gets confusing, try to think of some simple scenarios at first to get yourself used to it. For instance, if I'm standing right here in the airport and I'm watching someone go by on the moving sidewalk, that perhaps is going with a speed of 2 meters per second. Well, hopefully not, that would be really fast, but just for kicks. And then a person's walking on the moving sidewalk with a speed of 1 meter per second. Ask yourself, how fast did they end up going? You know that their speed with respect to the person standing here is going to be 1 plus 2, 3 meters per second. So sometimes it might help to think of simple examples to help you reason through how to do something that seems a little bit more complicated. Again, here we have the ground, and notice that we have the velocity, then we could write of the ball with respect to the ground would be equal to the velocity of the ball with respect to the truck plus the velocity of the truck with respect to the ground. Again, notice here how the T's would cancel out and I get B over G and they'd match. We can also do this in 2 dimensions. What if instead of just walking along in the same direction as the train was going, what if she walked across the train, like from the aisle into the window seat? Notice here now, here's the velocity of the train with respect to the cyclist is in this direction, but the velocity of the woman with respect to the train is in this direction. Notice that if we observe from a stationary point, she's going to be going at an angle. The velocity of the woman with respect to the cyclist ends up like this, at an angle. So while we first started off with things that were all on a line, we can also make these vectors and remember how we would add them as vectors if we had to, we would have to pay attention to x and y components. We would have to pay attention to, in this case I could just treat them like the Pythagorean theorem, and then I could use my trig to find my angle. But in the end, the relationship of the velocities is the same as what we saw in some previous slides. So hopefully that is helpful.